Hello everyone, I'm Johan and I'm going to present our paper, Lifting the Veil on Hyperparameters for Value-Based Deep Reinforcement Learning, in collaboration with João Araújo from Cohere and Pablo Castro from Google Brain. In this paper, we performed an initial empirical investigation into a number of often overlooked hyperparameters for value-based DRL agents, demonstrating their varying levels of importance. There have been a number of recent success stories in applied DRL to large-scale real-world tasks. But in all of these cases, very specific design decisions, including hyperparameter choices, were necessary for them to work effectively. Although tackling the same underlying problem, there exists a gap between academic and applied DRL. Many of the components used for large-scale real-world problems tend to be specific, resulting in less than ideal academic uptake. We argue that a key contribution to the gap between academic and applied DRL is a poor empirical understanding of the impact of the several hyperparameters. Mini-all introduced DQN, which combine Q-learning with deep networks. Some of the most salient design choices are: the Q function is represented using a feed-forward neural network, and a large replay buffer D is maintained to store experience transitions. On the other hand, Hessel combines several components like double Q-learning, prioritized experience replay, dueling networks, multi-step learning, distributional RL, and noise nets to improve DQN. This new agent is called Rainbow. To substantiate our claims, we revisit these hyperparameters in DQN and Rainbow papers in the hope that they help bridge this gap. In this project, we seek to answer the following questions. How sensitive are deep reinforcement learning algorithms to variation in hyperparameter selection? Does the choice of environments affect the sensitivity to hyperparameter selection? We perform our investigations in a low resource setting to investigate the effect of several hyperparameters. We evaluate on classic control environments like Carpal, Acrobot, Lunar Lander, and Mountain Car, as well as in the Miniature suite, consisting of 5 miniaturized versions of Atari games. These Atari games are Asterix, Breakout, Freakbait, Sequence, and Space Invaders. These environments are considerably larger than the 4 classic control environments, but they are significantly faster to train than regular ALE environments.
Hi, my name is João, and I'm going to be talking about how we divide our hyperparameters, some interesting results, and the main takeaways of the paper. So here we have our first grouping of hyperparameters that are those related to the network of our learning agents, to the neural network. So we have the initialization of the layers, the activation functions between the layers, the normalization, which is if you're using and what type, the width of the layers, and the depth of the network. And here we're going to be talking about specifically the normalization. We have some plots here. The upper row is the performance of DQN with Adam Optimizer and MSC as loss. And the bottom row is the performance of Rainbow, also with Adam, but with the distributional loss. Okay, and then for each one of these columns, we have a different Minotaur gain. In blue, you can see the default configuration, which is no normalization. In orange, here you have layer norm, and in green, you have batch normalization. So what we see here that is very interesting is that no normalization is pretty much the best in all cases, and in general, using normalization is extremely detrimental to learning. So we can see that, for example, for DQN, in all games except for Freeway, using batch normalization led to an awful final performance, pretty much a zero final performance. And either we have situations where there was no learning at all, or in some of them there was some kind of initial learning followed by a collapse of the agent performance. For Rainbow, we have more variation on that, but still, like we do see sometimes awful performance from batch norm and for layer norm. And so in general, the recommendation would be to not use normalization. And this is very interesting because for computer vision and NLP, we need normalization. We need layer norm for transformers. We need batch normalization for many of the state of the art neural networks used for computer vision. And here in RL, we see that the case is not that. That's the opposite case. Then we go for the optimizer hyperparameters. As I said, we're using Adam. And so we have the learning rate and the epsilon. The epsilon is that value that you add to the square root of the running average of the square gradients. So you add that. So you add the epsilon to avoid dividing by 0. But the thing is that epsilon is a value, and different values of epsilon can cause some different behaviors in the optimizer. More specifically, if you have a high values of epsilon, Adam starts to behave more like RCD plus momentum and loses some of the adaptivity. Okay, so what we see here that's interesting is that for DQN, we see a general robustness to the value of the hyperparameter. So we have I think three orders of magnitude difference from here to here. 2 orders of magnitude, right? So here, then divided by 10, then divided by 10. Yeah. And what this is that final performance is equal. Here we finally see some difference. So for a high value of epsilon in Sequest, we see that the performance does degrade, but it's still somewhat of a small degradation compared to what we see in Rainbow. For Rainbow, the large value of epsilon has awful performance in all of the 5 games. Like having a high value of epsilon completely destroys Rainbow's ability to learn. And so here the interesting part is the difference between the agents. So we had before the difference between RL and other fields of deep learning, and here we have a difference between the behavior of the agents. And now comes the algorithm hyperparameters. So they are the hyperparameters related to our algorithm, be it DQN or Rainbow. And you have reward clipping, the discount factor, the gamma, the minimum replay history, the update horizon, update periods, and number of atoms. This is only for Rainbow, obviously. So here we're going to be taking a look at the update horizon specifically. This is part of the multi-step return. So when you have the Bellman equation, you use one return plus the Q of the next step. And here we're going to be using many returns and the Q of many steps later. Okay, and what we see here is a difference in behavior from environments. So for both Rainbow and DQN in these 4 initial environments, if you use an update horizon of 3 to 5, you end up getting great performance. 3 or 5 are very close to each other in performance, and yeah. But for Sequest, you need to use update horizon of 10 or some high value higher than 5. And we see that there's a huge difference in performance from using 10, which is this curve here, to using 1, 3, or 5, which are these curves very down below here. Same thing for a Rainbow, high value of 10 as the update horizon has a much better performance than 1, 3, or 5. And so what these 3 things, what did they mean? What do we get from them? So first of all, we see that you can't just copy the ideas you get from other areas of deep learning into RL. This may be an interesting initial step, but if you're going to be using things for a more practical use, you do need to test. Here we see that you can just copy hyperparameters from one algorithm to the other because their robustness is very different to algorithms, and sometimes the best value for one is not the best for the other. And here we can see that you can't just copy the hyperparameters from an environment to another, because again, the best one can be very different and the difference in performance can be substantial. And from this, you get that environments matter. So if you're changing the environment, you should probably test your hyperparameters again. Just copying hyperparameters can lead to bad results, which is what we saw in these couple last experiments. And the network architecture and optimization are important. So this part here, for people that are coming from deep learning in general, may find that obvious, but we can see that in many RL papers, we have an analysis of a new algorithm technique, but the network architecture or the optimization, they're like, oh no, this is just the standard, which comes from, well, folklore pretty much. And optimization, we even had a change from RMS prop to Adam that wasn't mentioned at all. Like, people just started changing, and this also had a relevant impact, but it wasn't studied until last year by revisiting radio paper. So yeah, come to our poster session. We have many more experiments. We have many more interesting insights. And thank you very much. Muito obrigado.
I'll just start with the first question to the first authors, João. The question is, like, is grid search a good way to find these hyperparameters? If yes, is there any? If no, is there any better way of doing that?
Okay, hi. So grid search suffers from some combinatorial explosion. So as you increase the number of hyperparameters you're searching over and the amount of values you're searching for each of them, you get just a ridiculously number of combinations. And so it's often not really practical. What I would recommend would be to try something like Bayesian optimization. And there's like Vizier AI from Google that does that. There are some libraries that also do that. And you can try that, or you can try doing that up to some point, getting a couple of results as your bounds, let's say, and then you do grid search on these smaller bounds that could help you have like a more tractable number of combinations.
Okay, thanks for your answer.